Maverick Inventor versus Corporate Inventor, where will the next major innovations arise? Introduction: Technological innovation has been advanced by several sectors of human society and via a diverse set of circumstances. In the early 20th century, the solitary Maverick Inventor was responsible for the bedrock of most of today's industrial and commercial enterprises. As these enterprises grew larger, they could afford their own research and development departments, tasking them with developing products and processes aimed at increasing the market share of the parent company. Generally speaking, as time went on, these types of enterprises became less hotbeds of true innovation than places where improvements to the current technologies were tightly managed. Such management became stultifying for many inventors wishing to produce true innovation, and these mavericks shunned the commercial research agencies and went off to carry out their own brand of research. Another institution where true innovation is fostered is the university. University research as it exists today started in Europe only in the 18th century. The bulk of the discoveries in science leading to technological innovation came from university research laboratories in the 19th and early 20th centuries. Currently there is considerable controversy surrounding the degree to which research at universities is free from external influences, whether from within the university, from the greater scientific community, or from public and/or private agencies that fund the research. As university salaries and expenses go up, there is increasing reliance on external funding sources, the majority of which wish to exert some influence over the type of research they are underwriting. Human aggression and human needs gave birth to two additional areas of innovation. As governments became embroiled in conflicts, they found the need to fund think tanks for the purposes of stimulating scientific developments that could aid war efforts. As well, the needs of their constituents for food, shelter, health care, energy, economic development, space exploration, and so forth demanded the establishment of government-funded agencies to perform research and produce policy. To be effective, military planners needed access to the most innovative technologies in all areas of endeavor, not just armaments, and so established their own research and development departments. Circumstances determined the temporal requirement for innovation. Modern versions of the Four Horsemen of the Apocalypse, wars, pestilence, lies, famine/death, read conflict, environment, economy, health, pretty well sum up the major stimulants that foster innovation. Fortunately, human society, at least so far, has shown a remarkable propensity for inventing methods of overcoming seemingly insurmountable obstacles. This paper concentrates on two areas of technological innovation where solutions have been particularly hard to come by, namely energy and propulsion, in particular aerospace and space propulsion. It is now the case that new and exotic materials and their dimensions are driving the quality and quantity of energy and propulsion innovations and preventing the average inventor from contributing new and useful forms and assemblies. The capital outlay required to probe the limits of current high technology in search of a new breakthrough is also beyond the means of the vast majority of lone inventors. These are the major reasons for the shift in focus from the lone maverick inventor to the corporate inventor, the latter being a part of a large organization. This paper compares the roles of the maverick inventor who is less constrained by the strictures of a large organization with those of the corporate inventor and provides some insight into where to expect required future innovations in the areas of energy and propulsion. Maverick inventor: most of the easy combinations of components and materials have been investigated repeatedly since the time of Michael Faraday. However, it is still to this low-hanging fruit that the average maverick inventor is drawn for inspiration. For example, in the area of energy innovation, it is still attractive to many inventors to try various combinations of permanent magnets and wire to try to improve the efficiency of modern electrical machinery, or better yet, claim to extract possibly limitless energy from these magnets. The average energy inventor is not bothered by pesky laws of energy conservation or that the devices he is spending endless time on have been investigated hundreds of times before. There is also the role of the media, most important the internet, in continuing to stimulate the creativity of the maverick inventor. Movies continue to depict the lone genius saving the planet via some invention, be it a physical weapon or a piece of computer code. This no doubt propels succeeding generations to believe that they may one day single-handedly develop a new free energy or anti-gravity device and save the planet. Unfortunately, the internet has fostered the belief that new inventions, especially in the areas of energy generation and gravity control, are relatively straightforward, one simply needs the correct combination of macroscopic components. One of the disadvantages of the access to apparent technological innovation that the Internet provides is to foster and maintain intellectual and experimental laziness. This manifests itself in many ways, principally in that the prospective inventor increasingly believes that simply spending a few minutes on the Internet can give him all the background information about who has done what in a particular field of invention. Indeed, the would-be inventor does not even need to leave his chair and physically investigate the situation himself. A corollary concern is the lack of information on prior attempts that is available to maverick inventors. Whereas the corporate inventor has immediate access to a broad range of technical resources, including patents and scientific and technical publications, the cost of these resources and their publicly accessible concentration in university libraries drive the average maverick inventor to rely solely on the Internet. Fortunately, there are now positive signs that at least as far as free energy and anti-gravity are concerned, there are Internet sites trying to be repositories for failed inventions in these areas. Reference 1, 2. Another major problem is the decreasing reliance on a sound technical education, either in the sciences or in engineering. Why bother enduring 4 years of an extremely difficult undergraduate program when all the answers are right there on the computer screen? It is the age of instant, albeit self-proclaimed, geniuses. No need to bother with correct measurement procedures or proper control experiments when you can publish the results of your studies on YouTube without bothersome peer review. So how might one characterize the maverick inventor? Useful categories of maverick inventors, assumed to be in the context of the late 20th and early 21st centuries, might include the following types: individual with no formal training and little money. Individual with no formal training and some money. Individual with formal training and little money. Individual with formal training and some money. Small group, usually 2 or 3, of knowledgeable inventors with money. Formal training is assumed to be in the specific scientific or engineering discipline in which the invention would naturally be situated. Of course, in the last entry in the above list, the maverick inventor begins to look more like the corporate inventor, but the idea should be clear. Although this paper does not dwell on the personality of the maverick inventor, it is useful to remind ourselves that the maverick inventor is by definition a loner both in social and scientific/technical areas. In an online article, reference 3, Maverick inventor Dean Kamen 1 writes, "W's not that they're brilliant or well-educated, they work all the time. They don't let failure demoralize or destroy them. They pick themselves up and keep going, and eventually, every once in a while, one of your ideas actually breaks through and works, and it makes all that stuff seem worthwhile." Kamen's article goes on to state, "Stubborn, delusionally optimistic, creative, fearless, flexible and focused are some of the ways psychologists and business people describe the personality of the maverick. You need to be in denial or in ignorance about the huge challenges you face." Lasky Kawasaki, a former Apple executive and entrepreneur who's starting the self-described magazine rackalltop.com. You have to believe that it wouldn't be hard for you to succeed. Corporate inventor. The corporate inventor is a part of and relies on a large organization, conveniently labeled a think tank, to both stimulate and sustain him. There is constant interaction between like-minded innovators that serves both as a stimulus to explore new areas and as a much-needed dead-end detector. Usually, sufficient cash and equipment are on hand, especially when the desired innovation is being funded externally. These think tanks may be government, military, academic, corporate, or private. The closest model to the freedom associated with the maverick inventor is usually found in a university setting, although a number of privately sponsored institutions exist, for example, Perimeter Institute in Waterloo, Canada. At least until recently, academic institutions prided themselves in the freedom granted to their research scientists and engineers. Table 1 provides examples of the various types of think tanks. Dean Kamen is an experienced inventor in the medical field, where his inventions include the auto syringe. Among his many other inventions are devices using the Stirling cycle for energy generation and water purification and the Segway personal transporter. These entities typically arose in response to a particular need or crisis. Perhaps the most famous and effective think tank was the vast agency known as the Manhattan District. Less well known to the public was, for example, the Rad Lab at MIT. Except in the case of privately funded organizations, they all support many hundreds to thousands of researchers, of which a variable proportion could be termed inventors. Even the smaller entities support a dozen or so highly motivated scientists and engineers easily classified as inventors. A benefit of being an inventor in a large organization is access to information. The corporate inventor can quickly determine whether a certain avenue of approach has already been tried, using resources not generally available to the maverick inventor, such as patent searches, scientific and technical documents, or an in-house library. Another benefit is access to the latest technical apparatus, prototyping, and machining capabilities. In most cases, the inventor does not need to be an expert in the operation of all types of analytical or experimental equipment or machine tools. There are technicians at his disposal able to convert his ideas into reality. A relatively recent development in the larger organizations is the establishment of a blue sky team of highly creative individuals, sometimes just 2 or 3 people, whose job it is to think outside the corporate box and provide directions and policy, usually for the long term. However, in general, their tasks still fall within the general purview of the entity funding them. Sometimes government laboratories will allow such teams to investigate unusual areas and possibly set up experiments leading to eventual inventions assigned to the laboratory. A particular example is that of Tajmer, reference 4. Other relevant models for this type of activity are found in research and university hospitals, where continuous innovation is the norm. Corporate inventors also benefit from belonging to an organization that includes people with business acumen. An invention is worthless as a commercial innovation if it cannot be produced or marketed at a competitive price. The business side of the corporation is an essential component of successful innovation. The maverick inventor typically does not have these skills close at hand, and often the enterprise fails not for technical reasons, but because the inventor has not thought out an appropriate business plan. However, there are drawbacks to the life of the corporate inventor. Fluctuations in the overall economy can put projects on hold, cause them to be cancelled, or force layoffs that can stall or kill a project. The maverick inventor will strive to keep his project alive regardless of the external economy, which unfortunately sometimes means loss of savings, house, family, friends, and so forth. A not invented here, NIH, syndrome often can interfere with overall progress in areas where a corporate inventor approach is the most suitable. If an idea did not originate with a particular organization, it may not be pursued, even though it may represent the best approach. Maverick inventors rarely suffer from NIH. Whereas the maverick inventor is generally accustomed to putting 100% of his time into the invention, the corporate inventor may suffer from burnout if he is not as personally motivated or has such a personal stock in the invention. After a while, groupthink syndrome can infect large organizations, including their innovators. This happens in organizations that do not recognize or encourage radical thinking, resulting in mediocre innovation performance. This process is exacerbated if the number of projects being attended to by corporate inventors starts to overwhelm them. The maverick inventor is usually single-minded in his attention. Technologies. In order to gain a clearer understanding of the relative roles of the maverick and the corporate inventor, it is instructive to observe how each addresses specific technological areas. This paper concentrates on innovations in the areas of unconventional energy and propulsion systems as examples of ideas pursued by the maverick inventor in particular. The study does not focus on how the personality of the maverick inventor determines his innovative capacity so much as it focuses on what tools and techniques are available to him in addressing a particular potential innovation. The inventors highlighted in this study investigate technologies encompassing the production or conversion of energy from novel sources, sometimes referred to as new primary energy sources, including permanent magnets, cold and warm fusion, zero-point fluctuations, and novel uses of batteries and rotating systems, as well as theoretical and experimental approaches to modulating the local gravity field. Some of these inventors and inventions are described in recent books, see reference 5, 6. Historically, what has been the relative contribution to the major innovations in these areas? Taking the specific area of electrical energy production as an example, it was the contributions, inspiration, and determination of maverick inventors such as Tesla that resulted in the design of many of the current power-generating technologies in use today. As far as radically new recent designs of alternators and motors is concerned, there have been very few innovations from maverick inventors, Flynn's dual-path magnetic circuit being a notable exception, reference 7. Most of the innovations in this area come from corporate inventors in the electric power industry, as the only path left toward increasing efficiency is through novel materials such as high-temperature superconductors. Such research is generally out of reach of the Maverick Inventor. There has been no lack of attempts by Maverick inventors to produce electrical free energy and related machines. In the area of space propulsion and Earth-to-orbit methods in particular, again it was the contributions of mavericks such as Tsiolkovsky and Goddard that laid the foundations for modern rocketry. Both inventors took a practical approach to rocketry, as the field was in its embryonic state. Initially denigrated as being only a high school math teacher with no formal scientific training, Tsiolkovsky developed the fundamental equation for rocket propulsion. Although Goddard was university trained, like Tsiolkovsky, his fundamental work on rocket dynamics was largely ignored until later in his life. During their early, creative years, neither man worked for large organizations. As far as radically new propulsive means are concerned, there have been innovations only in the efficiency and overall design, and the fundamental mass expulsion model has remained unchanged. The efficiency innovations have sprung from corporate inventors who have the resources to plan and test their increasingly costly designs only in the context of large organizations. The current innovations in these two fields come from larger organizations such as those highlighted in the previous section. However, it should be noted that these innovations, largely increased in efficiency, had been economically as well as technically viable. There are plenty of novel thruster designs that would be excellent candidates for inclusion in the breakthrough category if only they were not so expensive. Antimatter propulsion using positrons and antiprotons is a good example, reference 8, 9. In the early development of electrical machines, many parts of the system were very expensive, electrical steel laminations, for example, but mass production brought prices down. Fortunately, inventions are not completely discarded simply because they are too costly at the time of their conception. Increasingly today, materials costs rather than manufacturing costs drive economic decisions about the development and commercialization of inventions in this category. This is due in part to the replacement of human manpower with its robotic equivalent and the scarcity of certain strategic technologically important raw materials, such as rare earths. The Type 1 Inventor. One should examine the area of novel energy generation inventions from the standpoint of the Maverick Inventor who has no formal training. Because the approach and timeline of the typical energy inventor mimic those of the propulsion, read anti-gravity, inventor, too, we will concentrate on the energy inventor. Often the invention involves a device that is purported to produce more energy than it consumes. In some cases the inventor naively thinks his invention is simply creating the extra energy from nothing. More often the inventor believes his device is tapping a new energy source, such as zero-point energy or magnetic energy. He typically begins his quest by literally playing with storage batteries or pulse-driven, simple, permanent magnet-based motors. Since the typical Maverick inventor has negligible funds for research and development, cheap measuring instruments are the norm. A very cursory understanding of electrical wiring and possibly a rudimentary capability in designing solid-state circuitry seem all that are necessary from an educational standpoint. Delving into thermodynamics, proper experiment design, error analysis, or even power factor is usually seen as taking valuable time away from construction of an invention prototype. Alas, it is most often in the area of measurement that the Maverick inventor solidifies his belief that he has discovered the answer to the world's energy problems. His fear of ridicule and belief that the local university or testing agency would, a. steal the invention, b. not do a proper test because they do not believe in the underlying concept, for example, zero-point energy, or, c. are in league with big oil and will suppress the invention, ensure that proper measurements are rarely performed at the important early stages of the invention's development. Fear of suppression also contributes to the typical inventor's lack of proper note-taking. The test instruments used usually are not suitable for use in measuring the various electrical parameters in, for example, pulsed motor designs. Even if more expensive oscilloscopes are purchased, their internal math functions are over-relied upon without giving a second thought to applicability, calibration, or use of proper probes within specification, among a host of bothersome details. The measurement problem is generally compounded when attempting to measure the true power or energy output of a device, especially where the output is a rotating shaft or source of heat. The modern Type 1 inventor shuns publishing in the peer-reviewed literature for obvious reasons and instead makes a YouTube video or appears on a TV weird science program or news clip to further promote this incredible invention. Up to this point, the invention has been developed using personal or immediate family funds. Once the Maverick Inventor is convinced he has the ultimate solution, the next step is to raise the necessary funds to produce a larger, higher power prototype. Note the key step of independently verifying the technical validity of the device at low power is to be avoided. Only a big power output will convince the skeptics is the slogan at this stage. And a high power prototype will take much longer to build, thus buying more time for the inventor to invent excuses for why the whole idea was unworkable in the first place. Usually the original prototype is either scrapped or robbed of components to make a new high-power device.